Alright, so today we're going over the Heisenberg uncertainty principle. Now, don't give me that look. I know you're scared, I know it's confusing, but by the end of the video, you should feel fairly confident about your understanding regarding this principle. Let's start with who Heisenberg was. He was born on December 5th, 1901, in Germany. He was a theoretical physicist and a pioneer of quantum mechanics, and is most notably known for his creation of the Heisenberg uncertainty principle. Now, of course, he formed this principle at the Bohr Institute in Copenhagen and officially published his paper on it in 1927. Now, of course, the point of the Heisenberg uncertainty principle is that it explains that there is a limit on how well complementary quantities can be determined. Now, that's a big mouthful. So, in order to show you visually what I mean by that, let's draw up an example. First off, we'll start with the formula that he uses. The uncertainty of position multiplied by the uncertainty of momentum is greater than or equal to h, which is Planck's constant, divided by 4 times pi. Now, since this quantity over here is a constant, these two values, as they fluctuate, they have to basically equal up to greater than or equal to this. If I decrease this one by a ton, so that it would be lower than this value, well, then I'm in trouble. I'd have to start increasing this one. So, if position goes down a whole lot, then my momentum has to go up. Now, of course, this is uncertainty of position. And if an uncertainty is going down, that means I have a better idea of where it is. For example, if I were to pass a laser through a very small hole, I'd have a really good idea that a photon that's traveling through this hole is gonna be in this general vicinity, this tiny little area. Now, of course, passing that photon through there usually leads into, well, not just usually, always leads to diffusion, as we covered in earlier in this course. So, even though I knew for this moment that the photon was right in this tiny area, I was fairly certain it was there. Somewhere, without knowing exactly where in that spot it was. Even if I knew that, I've lost track of where the photon went. It's diffused. I can't tell where it went, what momentum or velocity it had. Now, what's fun about this is that, going back to the momentum bit, the momentum can be substituted for, well, it's basically mass times velocity. So, I can actually rewrite this equation to become the uncertainty of x times the uncertainty of my velocity is greater than or equal to h divided by 4 pi m. Cool. Now, because of this, I can also say the opposite is true. If I have a general idea of where the momentum is, for example, if I knew there were a lot of photons traveling through this larger hole, and I knew they had this general trend of going that way, knew they were waving along that way, right? I could say with fair certainty, a fair amount of certainty, that the photon was going in this direction. Most of the photons were likely going in this direction. It's a very slim chance that it was not going in that direction. This uncertainty is very low. However, I have all of this space in here, and I have less and less of an idea of where it ended up in the spot it passed through. So, I can either know where it is, or at least I can either increase my certainty of where it is, or I can increase my certainty of where it's headed and how fast. Another illustration of this is a pulse on a string. If I send a little pulse through a string, I know where it is on that string. I know its position. But if I wanted to see how fast it was going, what its wavelength was, I wouldn't really be able to tell. Now, of course, if I sent a bunch of pulses so that it created a wave, I'd know the wavelength, so I could tell how fast it's going. But I wouldn't be able to tell you really, like, where is it? Where that little single pulse ended up in here. It's just kind of lost in the masses. So, position, momentum.